Welcome back. In this section, we'll be talking about inverse functions. But before we begin with that, we're going to first introduce the idea of a one-to-one function. One-to-one is referring to that every x value matches up with exactly one y value, and that's true for any function, but also every y value matches up with exactly one x value. So if we wanted to be a little bit formal here, we would say that if you have two different x values and f happens to be a one-to-one function, then you'll get two different y values. That's what a one-to-one function has as its properties. So for example, something like the cubing function, x cubed, that's one-to-one, because if you pick any two different x's, you will get two different y values. But that's not the case for something like the squaring function. You can have two different x values that come up with the same y value. For example, 2 and -2, they both have the same y value of 4. So something like the squaring function would not be a one-to-one function. So if you're just thinking in terms of what does that impact our function as far as the graph goes, if you're a one-to-one function, that means then for every x value, there's only one y value, and also vice versa. For every y value, there's only one x value. So if that's true, then that means that anytime you draw a horizontal line through your graph, it should pass through only one point. Because if it passes through more than one point, then that would mean you'd have two different x values with the same y value. And remember, for a one-to-one function, if you have two different x values, you need two different y values. So that's the origin of this horizontal line test. Remember, there's the vertical line test. Any vertical line should pass through the graph of a function in at most one place. If it crosses through in more than one place, then it's not a function because you have one x value with more than one y value. We also have the horizontal line test, which says that if you have a horizontal line that crosses through your graph and it always crosses through in at most one place, then it's a one-to-one function. If it crosses through in more than one place, then that means there are two or more x values with the same y value, then it's not a one-to-one function. So looking at the first one, f of x, y being x cubed minus x, you can see that this will fail the horizontal line test right away. If I draw a horizontal line through the x-axis, you can see that there's not just one place that we cross through, there are three places that we cross through. So this is something that's not one-to-one. 1 over x, on the other hand, that is a one-to-one function. Because again, if you're imagining any horizontal line that we draw through this, it will pass through the graph in at most one place. Same thing is true with my straight line, y equals 3x minus 1. That's also one-to-one. But this little half circle here, y equals positive root of 9 minus x squared, horizontal lines cross through this in more than one place, so this is something where it fails the horizontal line test, or in other words, it's not one-to-one. So the key idea here, why one-to-one is kind of an important thing, is again, it's that for every x, there should be one y that matches up with it, because it's a function, and if it's one-to-one, then every y matches up with only one x. And this little diagram here is kind of the idea that if you have a one-to-one function, you can reverse things. Instead of taking an x value and getting a y value as an output, you could do the reverse. Take a y value and get the x value as the output. Or in other words, we can look at the inverse of our function. What does the opposite or the reverse of what our function did? So that's the key idea here, that if we have a function that's one-to-one, then we can, in a sense, reverse that function. So what we can say is that we can define a function, f inverse, which does the reverse of f. So instead of taking an x value in our domain and giving us a y value back, f inverse does the reverse. It will take that y value and give you the x value in exchange. A couple of things just as far as notation goes. So just one key point here, even though it looks like this might be an exponent, it is not. So when you see f with a little -1, a function with a -1, that's not the reciprocal of f. This is not f to the power of -1. It is f inverse. This will also be true later on, by the way, when we start talking about trigonometric functions like sine of x and cosine of x, and we want to introduce inverse functions. We'll use the same sort of notation, inverse sine, inverse cosine, and so on. And in the same reason for that, that will also not be a power. That will represent the inverse of our function. So if we wanted to talk about the reciprocal of our function, because I know that that might be a question, well, how would you say f to the power of -1? You would have to write it like this, putting brackets around the whole function so that we're clear that, oh yes, it's the whole function that's to the power of -1. Or maybe to be less ambiguous, you would just write 1 over f of x. That's probably the clearest way to indicate that we're talking of a reciprocal of f of x. So anytime you see the f with a little -1, we should read that as f inverse. And again, what f does and f inverse, they exchange their roles. So for example, if f is a one-to-one function, and if f of 2 is 3, then that means it takes 2 as the input and gives you 3 as the output. That's what our function f does. So f inverse should do the reverse. It should take 3 as the input and give you 2 as the output, switching any x's with any y's. So this is one of the things I said in the end of 6.1. There was an example of two functions where when you composed them with each other, you got x. And I said to think about that for a minute and keep that in your mind when watching the video for 6.2. And so now it can be revealed that the two functions we looked at in 6.1 that had those properties, where when you compose them with each other, they gave you x, those are actually the properties for inverse functions. That for any function f that's a one-to-one function, then f composed with f inverse is equal to x, and f inverse composed with f is equal to x. This is how you can confirm that a function that you have and the inverse for it, that they are inverses of each other. So suppose I have my function f and I want to confirm that this is f inverse. I can do so by looking at number 1, f composed with f inverse, and seeing whether I get x as my result, and then also looking at f inverse composed with f. I have to do both, so it's not enough to just do one direction. I will need to do both, looking at f composed with f inverse as well as f inverse composed with f. So f inverse, that's cube root of x minus 2 minus 1. And I'm putting that into my function f. And in my function f, I'm replacing the x with that cube root of x minus 2 minus 1. So my original function f had x plus 1 whole thing cubed plus 2. And I've replaced the x with cube root of x minus 2 minus 1. And some things clean up right away. You can see that the minus 1 and the plus 1, those will cancel each other out. So we'll be left with cube root of x minus 2 cubed plus 2. And the cube root and the cube undo each other. and the -2 and the +2 cancel each other out. And there we go, we are equal to x. So for any x that's in the domain of f inverse, any x that you can put into this function will give you x as the output. And of course, if we're looking at f inverse, we should be able to realize that the domain for this is all real numbers. So again, any x that we want to put into this, any real number, will give us x as the output. So we have f composed with f inverse is x. Now we need to look at f inverse composed with f. So that's putting f inverse, putting f of x inside of it. And f of x, this was our function. Again, that was the x plus 1 cube plus 2. And so there we go. We're just going to now take our function f inverse, which, again, reminder that f inverse, that was our function cube root of x minus 2 minus 1, and we're going to replace the x with all of f of x. So instead of having cube root of x minus 2 minus 1, we're replacing the x with f of x, x plus 1 cubed plus 2. And again, just like the last one, things do simplify pretty quickly here. The plus 2 and the minus 2 cancel each other out. The cube root and cubing cancel each other out. And then the plus 1 and minus 1 cancel each other out. And so we're left with f inverse composed with f is equal to x. So there we go. We have confirmed by showing both of these, we've confirmed that yes, we are correct. Those two are inverses of each other. So we're going to now look at graphs of inverse functions and the relationship between f and f inverse. And so for this is something that, again, kind of comes naturally out of this idea that what f and f inverse are doing is switching the order in which we do things, that f takes an x value and gives you a y value, and f inverse gives you the reverse of that pair. So what that's telling us is that if you know that f of x has that point xy on our graph, then that means f inverse will have the point yx on our graph. In other words, whatever points you have on the graph of f, switch the coordinates, and that will be a point on the graph of f inverse. The other part that's also true is that f and f inverse, they're not just switching x and y values, but they're switching all x and y properties. So for example, if your graph had a vertical asymptote for f, that would be an x equals some number, that would be a vertical thing. That would be equivalent to, on our inverse function, having a horizontal asymptote of y equals whatever that number is. Again, we're switching all x's and all y's. So if your graph has a vertical asymptote, that's x equals, then on the inverse, you'll have a horizontal asymptote, y equals. It's also true that for your function f, whatever the domain is, those are x values, that will be the same as the range for f inverse, the y values. Again, switching x's and y's for all things. The other part that's kind of a nice little consequence of this, since we're f inverse really is just f where we've exchanged all the x's and all the y's, as it turns out, the graphs basically are mirror images of each other reflected in the line y equals x. All right, so now let's take a look at the graphs of f and f inverse. These are the same functions that we had confirmed were inverses a couple pages earlier. And if you were graphing f of x, you could do that with transformations. You know the basic shape of f of x. It's the cubed graph going through -1, -1, 0, 0, and 1, 1. And that you would have to take that graph and shift it to the left by 1 and up by 2. And if you did that, you would find that the graph of f of x would pass through the points -2, -2, 1, -1, 2, and 0, 3. So that would be my graph for f of x. And you can say a similar sort of thing about g of x. We know what the graph of g of x should look like because we know that it's basically a cube root graph that's been transformed by shifting to the right by 2 and down by 1. You know the cube root graph goes through 1, 1, 0, 0, and -1, -1. It has roughly that shape. And if you were to carry out those transformations to the right by 2 and down by 1, you would find that it would pass through the points 3, 0, 2, -1, and 1, -2. And again, just to point out the relationship that we have between our graphs, you'll notice that for f inverse, all of the points on f inverse are the same points that were on f, just with the x and y values exchanged. So for example, we have on the graph of f, there's the point -1, 2, and so on f inverse, there's the point 2, -1, switching the x and y coordinates. F had the point 0, 3. F inverse has the point 3, 0, again switching the x and y values. Also, if you're looking at the line y equals x, that would be the line that has a slope of 1 and a y-intercept of 0. You can see that my two graphs are mirror images of each other reflected across that line. And again, this is a property not just for these two graphs, but for any two functions that happen to be inverses of each other. That if you have a graph of f and a graph of f inverse, number one, they'll switch all of the x and y properties, and they'll look like mirror images across that line y equals x. Okay, so I've got a function here, f of x, and it's got a vertical asymptote. It has these 3 points, 4/3, -1, 2, 0, and 4, 1. And I'd like to sketch the graph of f inverse. The first part here would be for me to ask myself, do I even know that f inverse exists? And the answer is yes, this exists because f is 1 to 1. And I know that f is a 1-to-1 function because if you're imagining me taking any horizontal line and drawing it through my graph, it will pass through the graph in at most one place. That's it. It never crosses through in more than one place. And if it's a 1-to-1 function, then that means you have yourself a function that has an inverse. So we definitely can sketch the graph of f inverse. And I'm going to do that on the next slide. And it's going to switch all of my x and y properties. So first off, I know that because I've got these 3 points, 4/3, -1, 2, 0, 4, 1, because I've got those on the graph of f, then f inverse will have those points with all of those x and y values switched. So for example, instead of having the point 4, 1, we would have the point 1, 4. Instead of having the point 2, 0, we would have the point 0, 2. And instead of having the point 4/3, -1, we would have the point -1, 4/3. Just going to label these while I'm here. There we go. The other part is, again, it's going to switch all of our x and y properties. You have a vertical asymptote x equals 1 on our graph of f, so f inverse should have a horizontal asymptote of y equals 1. Also, if we're thinking in terms of domains and ranges, that gets switched as well. My domain for f looks like only values of x that are larger than 1, and so that means that my range for f inverse should be only values that are larger than 1. So this is why if you're looking at my graph of f inverse, why I don't have anything below that line y equals 1. And the reason is the range is values larger than 1 for f inverse, because for f, the domain was values that are larger than 1. Similarly, the range here is all real numbers. So that means for f inverse, the domain should be all real numbers. And yes, that's what we have. So this should be my graph of f inverse of x. So switching all of my x and y points, switching all of my x and y properties, and there we go. We now have our graph of f inverse.